We know from our examination of phase changes that there is a temperature at which the liquid and the vapor will coexist. We expect this temperature to depend on the pressure, so let's look at how the temperature and the pressure of coexistence for a liquid and a vapor depend on each other. Recall that the Clapeyron equation tells us that the derivative of pressure with respect to temperature for a phase transition is equal to the enthalpy per mole, change in enthalpy per mole for that phase transition, divided by the temperature at which that phase transition occurs, and the change in volume per mole for that phase transition. If we apply this equation to a vaporization, so if we have a liquid in equilibrium with a gas, then delta H for the phase change is the vaporization delta H, and delta V for vaporization is equal to the molar volume of the gas minus the molar volume of the liquid. But notice that the molar volume of the gas is going to be much, much larger than the molar volume of the liquid. And so we can write that the change in volume per mole for the vaporization process is approximately equal to the molar volume of the gas. If we now treat our gas as an ideal gas, then we can write that the vaporization change in volume per mole is equal to RT over the pressure. Making this substitution into the Clapeyron equation, we can write that dP dt is equal to delta H for the phase change per mole divided by RT squared times the pressure. Now, if we rearrange this so that we get all the pressures on one side and all the temperatures on the other side, in other words, separate variables, we can write that dP over P is equal to delta H of vaporization per mole divided by R times dt over T squared. Now what's left is to integrate both sides of this equation, and so we can write that the integral from our reference state, P reference, to any other pressure, dP over P, is equal to the integral from the temperature at the reference state, so that would be the normal boiling point of the substance, to any other temperature of delta H of vaporization per mole divided by R dt over T squared. The integral of dP over P is the natural log of P, and so if we evaluate that from P to P standard, we have the natural log of P divided by P standard is equal to the integral on the right-hand side of this equation. If we treat delta H of vaporization as constant with temperature, which is a reasonably good assumption for not too big of temperature changes, we have delta H of vaporization per mole divided by R, which are constant, so we can pull them out of the integral. And then we need to integrate dt over T squared, which gives us minus T, which we can then evaluate from T to the normal boiling point. This equation then gives us the coexistence curve for a liquid and a vapor. If we examine the approximations which went into developing this Clausius-Clapeyron equation, we will realize that the same equation can be used for the coexistence between a vapor and any condensed phase, so sublimation can also be treated in the same way. Notice that we made the approximation that the molar volume of the gas is much, much larger than the molar volume of the liquid. This will also be true for the molar volume of the solid. The molar volume of the gas is much, much larger than the molar volume of the solid, and so we can make the same approximation in our equation, leading to the same integration, except that in the case of sublimation, we're using the delta H of sublimation rather than the delta H of vaporization as we do for the liquid-gas coexistence curve.